Hey everyone, and welcome to our C5 live stream. So what we're going to do tonight is probably in about 40 to 45 minutes, we're going to go through a brief overview of all of those topics that could come up on your C5 test tomorrow. So we do have the chat window running there so that you can ask questions as and when you need to. I will try to obviously answer them when they pop up, but it may give me a little bit of time because I'm not always looking just at the chat window at that stage. Okay then, let's make a start. So what we'll find is that in C5 it's basically split into kind of three sections, if you like. So the first section has a lot of the calculations that we need to know. And the first one of these is all about percentage yield. The big difference between the chemistry papers and any of the others is that they don't tend to give you any of the formulas here. So when we say you need to be able to calculate percentage yield, you also need to know the formula for that. So percentage yield is the actual yield divided by the theoretical yield, and then we multiply it by 100 because this is a percentage, hence the name percentage yield. Hopefully pretty straightforward. So you've got to memorise that formula first of all. Then, in order to actually work this out, the first thing we could be asked to do is to calculate the theoretical yield. So in order to do that, what we need to do is look at our question and calculate the relative formula masses, first of all. So look at the atoms, get the periodic table out, look up each of those individual elements, write down their atomic mass, and then multiply by however many atoms of each there are. Then we calculate the sum of the relative formula masses using our balanced equation, and by that what we do is the relative formula mass of that chemical times the number of moles of it that exist. And then we can calculate the theoretical yield by using the mass of the limiting reactant divided by the sum of the relative formula mass for the reactant times the sum of the relative formula mass for the products. So that gives us the theoretical yield. Now, not all percentage yield questions will ask us to do that. Sometimes they will literally just say in the actual main body of the question, the theoretical yield for this is, and they'll give you an amount in grams. So in that case, all of that's kind of irrelevant because they just gave it to you. Then what we need to do is calculate the percentage yield. And in order to do that, all we need to do is the actual yield, so whatever they say the actual yield is, divided by your theoretical yield, and then multiply that answer by 100. Again, it will be a percentage, so that means your answer will be somewhere between 0 and 100. If it's not, you've probably put them the wrong way around. In all honesty, it's the easiest check ever that if once you've typed that into your calculator, you've got something coming in as something ridiculous like 532, just flip them the other way up and then you'll probably get it right. So what we need to do is make sure we know how to use our calculator. This sounds so obvious, but people fail time and time again to do this. So actual yield divided by your theoretical, push the equals button, and then multiply by 100 to get the actual percentage yield. What we'll find is a usual follow-up question once they've got you to calculate the percentage yield is they'll ask you reasons why it's not 100%. Because very, very few actual experiments will have a percentage yield of 100%. So three key things that you can actually put down here. First one is the reactants may react in a way that we hadn't expected. So they might react with things like oxygen in the air and therefore form different products. Second is the reaction may not go completely to completion. So some of the actual reactants are left over. And thirdly, we may actually lose some of the product. So that could be through evaporation, it could be through transferring the chemicals from one vessel to another, but product is lost in some way. Now, what we'll actually find is usually that would be worth maybe 1 or 2 marks. So if you've learnt all three, you're good and safe on that one. The second calculation we need to know then is atom economy. So the atom economy, quite simply, is just a little measure that we can use just to say how many of the atoms that we started with in our reactants actually form the desired product, so the product we intended to make. So we're looking basically at how efficient is this process at making the product we wanted. If we have a low atom economy, then that means there's very few atoms from our reactant that end up in the desired product. Whereas a high atom economy, then most of the atoms from our reactants end up in the desired product. So it's better to have a high atom economy. To work it out, again, there's a formula we need to memorise here. So the sum of the relative formula mass of the desired product, the thing we intend to make, divided by the sum of the relative formula mass of all of the products, and then we times it by 100 to give it as a percentage again. So what we actually find here is it's actually all to do with the products. The reactants we don't need to worry about in our calculation at all. So your desired product is always the one they're telling you in the question, this is what we intended to make, or in a process to make such and such. That's your desired product. That's the one we calculate first of all. Divide that by the relative formula mass of all of the products, and then we're just going to multiply by 100 to give it as a percentage. So we've got two different calculations there that we will see are generally used together in a question asking you which is the best process. So atom economy is all about how many of the atoms from the reactants make it to the product. So it's looking at basically how sustainable or how green this process is. Because if we've got a low atom economy, it's wasteful. We're pretty much throwing away our money. Whereas percentage yield is about the percentage of the product that we make, so the amount of the product we generate. So this is more looking at, rather than how many of the atoms from the reactants turn into the product, it's just how much product do we generate full stop, regardless of wastage. Now, we did mention there that these two could be used to help us select different reaction pathways, because as we've already found from the work we've done in C6, there's more than one way to make a chemical. So when we're actually looking at and deciding which kind of process to use to make our chemical, what we need to do is consider a range of these factors. First one, the yield. You want the highest yield possible. Second is the atom economy, again, highest one possible. Third, the rate of reaction, which we're going to look at a little bit later on tonight. Fourth one, are there any byproducts, and if so, are they useful or are they toxic? Because that can be a deciding factor in which kind of process we should use. And finally, when we're looking at some of these reversible reactions, what conditions do we need to move the equilibrium position to where we want it? So those are different things that we could consider, and the kind of question they like to give you here generally has a little table with some information about two different ways to make the same chemical, and they just sort of say pick a process and justify your choice. So you'd have a look, spot the one that's got the highest atom economy, the highest percentage yield, the fastest rate of reaction, say that's the one, and then you back it up just by saying, well, it's got a high atom economy, it's got a high percentage yield, it's got a fast rate of reaction. And then we can explain it by saying that obviously high atom economy means that less of the reactants are being wasted. High percentage yield means we're generating a large amount of our product. A fast rate of reaction means we're making it really quickly. So that then gives us a really good way to justify our answer there. You'd always want the high atom economy. There's no reason that you'd want to waste your reactants. Okay, next one is another calculation. In fact, it's kind of two calculations for the price of one, because we're coming on to look at how we calculate the concentration of a solution. Before we can jump into that though, we do need to know one of these really important conversions, and it's one that's cropped up in a few different places. Quite often in the chemistry papers, they like to try to catch you out because they will give you a volume in centimetres cubed. When we're doing calculations in chemistry to do with volumes, we want it in decimeters cubed. So you've got to actually divide your centimetres cubed by 1000 to get the decimeters cubed. So watch out for that, because it is one of their favourite little ways to try to trip you up there. So if it gives you 25 centimetres cubed, then 25 divided by 1000 gives us our decimeters cubed. Now, once we've actually got that, we can then go on to calculate our concentration. And as I say, there's two ways we can do this. First one is we can do the concentration in grams per decimeter cubed. And to do that, it's just the mass of our solute in grams divided by the volume of the solution in decimeters cubed. If they were to ask you to calculate the concentration in moles per decimeter cubed, then it's your amount of solute in moles divided by the volume of the solution in decimeters cubed. Now, the one in moles per decimeter cubed is the slightly trickier one, because they may actually get you to work out how many moles there are in the first instance. So to do that, you need to work out your relative formula mass, and then in the question it will tell you how many grams of it there are. So once you've actually got your relative formula mass, all you then do is the amount from the question divided by the relative formula mass of that chemical, and that tells you how many moles you've got. Then divide that by the volume in decimeters cubed, and you've got your concentration. Now the next bit is the bit you all don't like. It's titrations again. You all hated this when we did it in year 10, you hated it when we did it in lockdown, and it's coming back once more, you'll be pleased to know. Now, titration itself is just the method that we're going to use to determine the concentration of an acid or an alkali by using a neutralization reaction. So we use a single indicator, and the reason we use a single indicator is because it has that really clear endpoint. So a good example is phenolphthalein, if you can spell it. Now, that is really important because we don't use universal indicator, which is a mixture of several different indicators, because you need to know exactly when does it change. And universal indicator, as you know when I've given you these challenges to make me the universal indicator different colours, judging it is a nightmare. So we want it to go from one colour to a completely different one in one moment. That's what we mean by a single indicator. Now, titration is actually one of those practicals they could ask you about, including how to carry it out. So you've got to know that basic method. So we've got that big glass tube with a little tap at the bottom. That is our burette. So we fill the burette with acid, and obviously we put a little funnel in the top, put it on the floor, and then we pour the acid in, so we're not pouring acid above our heads. Then, in order to get our alkali, what we do is we use what's called the volumetric pipette. So you'll remember those, they're the big glass tubes where we had the little guns on the end, or you could have had the little kind of squeezy ball bits, but they've got a pipette filler. So they've got a fixed volume, usually 25 centimeters cubed is what we use in class. So once you've filled your burette with acid, you then use the volumetric pipette to transfer 25 centimeters cubed of your alkali, and you put it into a conical flask. Once you've done that, add a few drops of your indicator solution, give it a little swirl, and then you record your start volume from the burette. First time should be 0. What we then do is you turn the little tap at the bottom and you gradually add the acid from the burette into the flask. And as you're adding it, you need to do that swirl so it mixes. And we're looking for the point where it just changes colour. You then turn it off and read your end volume off your burette. Write that down, and that gives you your first titration. So the whole idea here is we know how much acid it takes to then neutralise the alkali. So we've got a volume. In terms of the kind of question they could ask us here, it could well be along the lines of, I'm trying to think of one I've seen in the past, a student wants to make a salt of potassium hydroxide, describe how they would do this, including the names of the acid and alkali they would use. So because this is just a neutralization, we just describe the method of titration there, and we'd name the acid and we'd name the alkali. So that's a good example. Now, one of the key things about our titration is that when we're actually carrying it out, you don't just do it once. Because as you found when you actually did this in class, you're pretty terrible at doing this. So the first time you do it, your actual result is shaky, to say the least. What we need to do is have not just one result, but we need to have our concordant titers. And by that, what we mean is that you've got results that are within 0.1 centimeters cubed of each other. So you've just got to make sure that you've got not just one result, but you've got 2 or 3 that are within 0.1 centimeters cubed of each other. And when we talk about a titer, that's just the measured volume of solution from the burette. Now, there are 3 kind of indicators I'd suggest you learn here. So the first one is litmus, and this one is red in an acid or blue in alkaline. So dead clear colour change. You'll start off with it being nice and blue in your alkaline solution, and then it will obviously flip over to the red colour. Dead easy to see that one. Second, phenolphthalein, that's the one that's a joy to spell, and it starts off with the pink colour and it will go colourless, okay? Or obviously if you've got it the other way around, then it would go colourless and change to pink. And then finally methyl orange is red in an acid and yellow in an alkaline. So just make sure you pick a suitable indicator. You can name any of them, in all honesty. So if you can only remember one, pick the one you can spell. That's absolutely fine. Now, what we also need to do is, before we can carry out our titration, we need a standard solution. And that's just something with a known accurate concentration. So basically, before we start this, we make a solution ourselves. So you carefully weigh out the actual amount in grams, you add it to a very carefully measured volume of your water, and that gives you this known concentration. They're not generally going to ask you about how to do that, so we're not going to look at it too much here. They could, however, ask you about how to improve a titration. So they'll give you a little method, they'll print it out and say, students doing an experiment, here's their method, and then they say, how could they improve it? So things to look out for here are, did they measure using a measuring cylinder instead of a volumetric pipette? Because measuring cylinders are far less accurate than the volumetric pipette. So you could say they could swap the measuring cylinder for a volumetric pipette. You can have a look and see, did they clamp the burette perfectly vertically? Because if it's on a slight tilt, when you read the actual values, it's not going to be that accurate. You also need to comment about the fact that when we come to read the burette, because it's in a narrow tube, it's not completely flat. You end up with something more like this. So that is actually our tube of our burette, and the solution forms this curve here. Now this is a curve called a meniscus, and when we read it, we need to read from the very bottom of the curve. Okay, so you don't read from the top bit here, you read from the bottom down there. So you've got to get eye level with that in order to read accurately. For the extra accuracy, we normally go to 2 decimal places here. So what we find is, if the bottom of that meniscus sits perfectly on one of the lines on our burette, then the second decimal place is always a 0 because it's spot on. If, however, it's part way between the 2 lines on the burette, then the second decimal place is a 5. So that just gives us 2 decimal places of accuracy for all of our readings there. The only other thing to mention there is that you should always swirl the flask in order to mix the contents, and make sure that as you approach your end point, you add it a drop at a time, because if you don't do that, you overshoot the end point and we have to start all over again. And you are well practiced in that from when you did it in class. The next bit is the calculation side of titrations. So when we've actually carried out a titration, what we need to do is then carry out calculations using those values. So again, they could ask you about how to do the titration and then go into a calculation, or they might just give you a calculation question straight off. So once we've actually done our titration, we know a few things. Firstly, we know what 2 reactants we used. Secondly, we know the volume and concentration of one of those reactants. And finally, we know the volume of the other reactant there, the second reactant. From that, we can actually work out the concentration of our unknown chemical. And the way we do that is in our delightful little calculation, which we can put into our nice little triangle. So this is one we've got to learn, folks. Okay, there's our triangle. So N is just our amount in moles, so the number of moles. Then our concentration is the C, and V is the volume. So the amount in moles is the concentration times the volume. If you know this triangle, then you're halfway there to answering any of the calculation questions, because all we do is we just use this same triangle over and over again. Okay? So the first thing you are going to have to do in, I would say, every question I've ever seen is convert the volumes to decimeters cubed. So any of the volumes they've given you, convert them to decimeters cubed by dividing by 1000. Once you've done that, then what we actually have is, for one of those reactants, remember, we know the concentration and we know the volume. So we've got those 2 bits of information that we can put into this. Because if we've got the concentration and the volume, we can just multiply those two together and we get the amount in moles. So for one of our reactants, we now have the amount in moles, the concentration, and the volume. Even if that's as far as you get, you've picked up marks on this question. After that though, we look at our balanced symbol equation, and they usually give this to you. And we're looking at our ratios. So if 1 mole makes 1 mole, then quite simply whatever your amount in moles was from your little calculation we just did would be the same for the other one. If however your 1 mole makes 2, you just multiply it by 2. So it's just literally getting those same proportions there. Once we've done that, we've then got the amount in moles and the volume of our second reactant. So all we can then do is the amount in moles divided by our volume in decimeters cubed, and we get our concentration. And you're done. So it's not as bad as we think, it's just using that one triangle a couple of times over. The last calculation that we need to do is the gas calculations. Now, when we're looking at this, what we're looking at initially is the molar volume of a gas. Now, molar volume, quite simply, is what we're talking about with 1 mole of any substance in the gas state, and it will always occupy the same volume at the same temperature and pressure. So no matter what chemical it is, if we have 1 mole of it, and it is in the same temperature and pressure, it will always occupy the same volume. Whether it's oxygen, nitrogen, carbon dioxide, makes no difference. So that's what we mean by molar volume. And the number to remember here is 24, because at room temperature and pressure, which is sometimes abbreviated down to RTP, then this is 24 decimeters cubed per mole. So that's all you need to know, is if they ask you about what the molar volume of any gas in the world is at room temperature and pressure, 24 is the answer we go with. Now, once we've got that, we can also work out how much space, so what volume, any amount in moles of a gas would occupy. Because what we then have here, we've got our volume, our amount, and our 24. Again, we can chuck it in the triangle. Sorry about the terrible handwriting there. But if we've obviously been told we've got 5 moles of a chemical and they want to know about how much volume it will occupy, we just do 5 times 24 and we get it. If they give you a volume occupied by a gas and ask you how many moles it is, then all we do is whatever volume they gave you divided by 24, and that gives you your amount in moles. So just remember, room temperature and pressure, it's 24 decimeters cubed per mole. As for why it's 24, it just is. That is just a scientific fact. There is no particular reasoning behind it. We've measured it and it occupies 24 decimeters cubed per mole. So that's our first section, the calculation-y bits out the way. Section 2, I think, is the nice bit of C5. It's all about rates of reaction. So this is where we can learn a couple of key points and then we can get really high marks on virtually any question we've got here. When we're talking about the rate of reaction, we're just looking at how we can measure the rate at which our reactants are being used or the rate at which our products are being formed. So all we need to do is the amount divided by the time. So if you want to know about how we write decimeters, it's just dm with a little superscript 3. So dm cubed is decimeters cubed. Now, when we actually come to measuring volumes, then what we've got are a few different ways we can do this, because we're talking about measuring volumes of gases in virtually all of the experiments they could ask us here. We do have the first and most useless way ever, which is counting bubbles. So any experiment they tell you where someone is counting bubbles, then it's completely inaccurate, because the bubbles are all different sizes and you're really likely to miss them when they're coming quick. Option number 2 is our upturned measuring cylinder. So we fill the measuring cylinder to the top with water, put it underwater in a little sort of trough or ice cream tub, turn it upside down, and then put the delivery tube just underneath it. All the gas that's made goes through the delivery tube and it displaces the water. You can just read off the volume from the measuring cylinder then. Better, but we could have the little delivery tube slip out, so some gas could be lost again. The best way is using a gas syringe. So that's literally a device that is a big glass syringe that connects onto our conical flask, and all the gas made goes straight in. You can read it off. So if they give you any experiment that makes a gas and ask you how to improve it, use a gas syringe is always the answer there. So that should be a nice easy one marker somewhere on a paper. They could throw in the maths content here. Now, hopefully we remember that 10% of your marks on the overall exam papers will be for maths. So it could be the calculations we've looked at already. It could be for actually calculating rates from a graph. If they're asking you about the mean change in rate, then that's literally just calculate the gradient of the line between those 2 points. So whatever the time is that they've given you, all you do is you read what the volume of gas is at the start, you read what the volume of gas is at the end, work out the difference between it, and then your change in volume divided by the change in time. So that's the mean rate. If they're being mean on the higher tier usually, then they could ask you what the rate is at one specific point. So what we then have is we'd have our little graph like this, and they'd ask us what is the rate of reaction at, say, that point there. Okay, so it might be at, say, 60 seconds. So you can't draw the triangle for this. Instead, what we have to do is using a ruler, and I haven't got a ruler, so just imagine it's a nice straight line here. So using a ruler, what we do is we draw our own tangent to the line. Okay, so you can see there's a lovely straight line, imagine, and it's running through that point. So you literally place your ruler on that point, and then you need to make sure the two sides are pretty equal from the line. Once you've got that, we can then turn it into our little triangle to work out the differences. So as soon as you've got that, we can then just basically do the same as before, work out a change in time, a change in our volume, and then just divide the change in volume by the change in time. And that gives you that rate at that one point in time. The next bit is looking at the actual experiments. Now there's a range of different experiments they could give you here. Some you've done, some you haven't done, and it doesn't really matter. Because what we're really looking at here is how we can then explain the results. I can't think of an experiment where they've actually asked you to say how to do it for this. So it's more a case of they're going to give you some information from the experiment itself, so the results, and then what we do is explain it using our scientific knowledge. The way you know what angle to put the line at is once you've placed your ruler at the point, then just either side of it, make sure, because it will be a curve, then just make sure it's about the same distance between the ruler and the curve on either side. It's not going to be 100% perfect. There will always be a range given to you for your answer there. So let's look at these factors that affect rate then. First one is temperature. Hopefully we do know that if we increase the temperature, then the rate of reaction will increase. So that would always be worth our first mark. Increase in temperature increases the rate of reaction. And the reason for this is that when we increase the temperature, then the particles will gain kinetic energy. That means they're moving faster and they will have more frequent successful collisions. That's our phrase for the day. More frequent successful collisions. Those 4 words are going to get you a lot of marks on the rate section. What we will then find is that is the sum total of our explanation for temperature. Increase in temperature increases the rate, the particles gain kinetic energy, so they move faster, and there are more frequent successful collisions. If you wanted to take it that final step just to make sure you've covered every potential base, you could say that the reason the collisions are successful is because more of them will exceed the activation energy. Done. Factor number 2 is concentration. So concentration is just a measure of how much solute is dissolved in our solvent. So a more concentrated solution has a greater mass of our solute dissolved there. When we increase the concentration, then the rate of reaction increases again. So the reason for this is that in those higher concentrations, we've got more particles in the same volume. So the particles are more crowded, and that means there are going to be more frequent collisions. So we're seeing a theme here, I hope, that when we're seeing this increase in the rate of reaction, then we have more frequent collisions. The next bit we need to consider is when the reaction will stop. and quite simply, it's when the limiting reactant is used up. So the way we can always tell this on a graph is that when we look at it, then we don't have a never-ending line. Instead, it levels off. So you can see it's plateaued. And by plateaued, we mean it's gone horizontal over here. So this is the point that our reaction has come to an end. Our third factor is one for gases, which is pressure. So if we're talking about reacting gases together, then pressure is a factor. And if we increase the pressure, the particles become more crowded, so there are more frequent collisions, and therefore the rate is faster. Same things again, more frequent collisions. Our next factor is surface area. So what we actually find is that when we've got a solid material and we break it up into smaller pieces, then the surface area will increase. So when we look at that in terms of things we know, a powder will have a larger surface area than a single lump of rock, for example. When the surface area increases, then the rate of reaction will increase. So that just means that we've got more actual space exposed to the particles. So the greater surface area means that we've then got more exposed particles, so we have more frequent collisions. And that means our rate of reaction will go up there as well. The last factor we have are catalysts. Now, we hopefully know the definition for a catalyst. It's usually a two-marker. First one is for saying that it's a substance that increases the rate of a reaction. Second mark, but it's unchanged at the end of it. So know that definition, because not only is it going to increase the rate, but it needs to be unchanged. So what we can actually see there is that if they were to give you a table of different chemicals, they would tell you the rates of them. They would tell you things like their colour at the start, their colour at the end, their mass at the start, their mass at the end. So all of that would then allow us to pick out the one that is a catalyst, because the rate would increase and we'd see that the colour stayed the same, the mass stayed the same. Key thing about our catalysts is they are specific to a reaction, so they only work for the one chemical reaction there. If we add a catalyst to our reaction mixture, then the rate of reaction will increase. And the reason for that is that we end up with an alternative reaction pathway. And this alternative reaction pathway has a lower activation energy. So this is where we can come back to our little bits that we looked at back in C3 with our reaction profiles. So we've got the activation energy is this bit here, so the bit that goes up to the top. If we obviously add a catalyst, what we end up with is a lower activation energy. There we go, so the little dotty line there. And that means that a greater proportion of the colliding particles will exceed the activation energy, and therefore they will react. So reaction pathways are literally just looking at the different methods that we can make chemicals. Right, the last section, our reversible reaction section. You really don't like this bit when we've done it several times over, but hopefully you're getting there now, okay? Activation energy is the energy that we need in order to actually start a reaction. So every chemical will need a certain amount of energy to actually allow a reaction to take place. That's the activation energy. Now, when we talk about reversible reactions, this is one where once we've made our products, then the reactants can reform. And the key symbol we need to know for it is this one. So half an arrow going one way, half an arrow going the other way. So they've got both a forwards and a backwards reaction. Now, we've had a look at several different examples by now because we've looked at several of them in C6. When we're looking at these, what we're really concerned with is something called the equilibrium. Now, what we find is that in a closed system, so one where nothing can escape or enter, then we've got the ability to set up an equilibrium. What that means is when it is at equilibrium, the forward reaction and the backwards reaction are equal. So the concentrations of all of the reacting substances will remain constant, okay? we go one step further and actually say that it's called a dynamic equilibrium, because it's not static. It's not like it gets to this point and then everything just stops. The forward and backward reactions still happen, therefore it's dynamic because things are still going on, but it's in equilibrium because our concentrations of those reacting chemicals remains constant. When we actually come to describe equilibrium position, then we're looking at our relative amounts of the reactants compared to the products. And we will always describe it as being either on the left or on the right. So whenever we're looking at a question that says which direction will the equilibrium position move, it's either going to be left or right. So even if you don't know, you've got a 50% chance of guessing. So if the equilibrium position is on the left, then that means the concentration of reactants is greater than the concentration of the products. Whereas if the equilibrium position is on the right, then the concentration of reactants is less than the concentration of products. And what we can actually do is we can change this based on different conditions. So the first condition we can alter is the pressure. If we increase the pressure, then the equilibrium position will move in the direction of the fewest moles of gas. So to work this out, we look at our balanced symbol equation, and what we will find is they will have state symbols. And the only ones you need to worry yourself with are any chemicals with the little g in brackets telling us they're a gas. So we look at how many moles of each of those gases there are on the left, and how many moles of the gases there are on the right, add up your totals, and then if we increase the pressure, what's going to happen is it's going to then move in the direction of the lower number. So if we had 3 moles on the left and only 2 moles on the right, increasing the pressure would move it to the right, because that's the fewer moles of gas. Second one we can do is concentration. And if we increase the concentration of a substance, then the equilibrium position moves away from that chemical. So if we increase the concentration of one of our reactants, then that means the equilibrium position moves to the right, away from the reactants. Whereas if we increase the amount of our product, then the equilibrium position would move to the left, away from the one that's increased in concentration. Third one is our temperature then. And if we increase the temperature of a substance, then the equilibrium position moves in the direction of the endothermic change. So what we do here is we're looking to the side of our equation where it will have a number, usually in brackets, that is called delta H. Okay, this is our enthalpy change. If it has a negative sign in front of it, that means the forward reaction is our exothermic reaction. If it's not got the negative sign, then the forward reaction is endothermic. So that's your first bit, is identify, is the forward reaction endo or exothermic. Endothermic doesn't mean cold. Endothermic means it's going to take in energy from the surroundings in order to actually carry it out. So if we then increase the temperature of our substance, it will move in the direction of the endothermic change. So either to the right or to the left, depending on which one is endothermic. Now, what we actually find then is you would be asked potentially to suggest conditions or suggest why they've selected certain conditions here. Now, obviously, what we need to do is think about how much is it actually going to cost us to generate these conditions first of all. So when we've looked at pressure, remember what we've said. Sometimes, yes, okay, increasing the pressure does increase, obviously, our equilibrium position because it's moved it to the right, so we've got more of our yield. But there comes a limit, because high pressures require obviously specialist equipment, they require large amounts of energy, it makes it very costly. So you get to a certain point and you just think it's not worth it anymore. If we're looking at something like the temperature, again, we need to have that balance. So we can either have it as a very high temperature, which obviously means in some cases we're decreasing the yield, but we don't just want to put it at the lowest temperature possible, because even if that does increase the yield we'd make, it would take a long time. So we've got to balance that rate of reaction with the high temperature versus the equilibrium position being shifted too far to the right, okay? So make sure you do think about those balances. And that's it. That is literally all of C5. So what we've actually gone through there then, all those different calculations you need to know, rates of reaction bits where our favourite phrase is going to be more frequent collisions, and then finally just the equilibrium position. So knowing the reversible reaction sign, knowing the 3 different conditions that can affect it, and obviously how we can kind of manipulate those conditions to suit our purposes in a reaction. And we're done in 40 minutes. There we go. That wasn't too bad. So obviously tomorrow is your test, okay, whether you're in W or E, doesn't matter, you've both got the test, and you are probably going to need a calculator. So calculators with you, and obviously just your standard pens. And let's just make sure that go over any of the bits you weren't 100% certain on. Obviously, we've got the videos on the channel that you could have a look at those specific bits. You've got your books. And other than that, good luck for tomorrow, folks. Have a good evening, and I will see you at school.